Good morning and welcome to our series of videos on dose ratios and monitor unit calculations in radiation therapy. I am Jeremy Pulf. I am your host, and this is part one in our series in which we will cover some basic concepts for dose ratio and monitor unit calculations and learn what the percentage depth dose is and how it's used. Our objectives for this series of videos is to understand the basic concepts underlying dose calculations for radiotherapy, to recognize and understand some fundamental quantities that are used to describe the basic dose calculation concepts, and in our final video, we will apply what we've learned to calculate the monitor units needed for a clinical radiation oncology treatment situation. So, let's start with how we would calibrate a treatment linear accelerator. For our cute little LINAC here, what we would do is we would take a calibrated detector, like an ion chamber, and stick it in a water phantom at a fixed position and measure the dose delivered to the ion chamber for a fixed set of beam delivery conditions. So we would start with a calibration statement which defines our entire calibration setup. For instance, for a 6 MV X-ray beam with the phantom set at a distance of 100 centimeters from the source at a depth where the dose is at a maximum within the phantom, and for a 10 by 10 cm field, what we would do is adjust the output of the LINAC for those conditions such that one monitor unit delivered by the LINAC is equal to 1 centiGray recorded by the ionization chamber. You might be asking yourself, what is a monitor unit? Well, an MU, or a monitor unit, is a discrete unit of charge measured by the LINAC's dose monitors. So it's a measurement of the beam intensity by the LINAC itself. So, after we have calibrated our machine according to the conditions defined by our calibration statement, what we know is the dose delivered per monitor unit recorded by the machine for a single field size and at a single depth or position within our patient. However, for treatment conditions, what we want to know is what is the dose at the depth of the tumor within the patient, and for the field size that we're going to use to treat that tumor. And these conditions are often wildly different than the conditions outlined by our calibration statement. So, over the course of this videos, we will go over the process we use to convert from the dose we know at the calibration condition to allow us to calculate the dose delivered to the patient under treatment conditions. So, what can change when we go from calibration conditions to the patient treatment conditions? Well, as we've already alluded to, the distance from the source to the point where we want to know dose can change, the depth within the patient, and the field size used to treat the patient. And these all have an effect on the actual dose delivered to the point we want to know within the tumor. Let's look at how the field changes as we move further away from the beam source within the LINAC. Our treatment field diverges. That means the field size increases as our distance from the LINAC increases. The field edge is proportional to our distance from the LINAC. So that means the ratio of the field edge at point 1 to the field edge at point 2 is equal to the distance at 1 to the distance at 2. So for instance, let's say our field edge 1 is 10 centimeters and our distance 1 is 100 centimeters from the source. What is our field edge size if our distance from the source increases to 200 centimeters? Well, we know that the field edge ratio is equal to the distance ratio. So if we plug in our numbers, known numbers here, and we rearrange our equation, we can calculate what the field edge size is at distance 2. Aha, 20 cm. So we see that as the distance doubled from 100 to 200 centimeters, the size of the field edge doubled from 10 centimeters to 20 centimeters. Also, we see that the intensity of the treatment beam is inversely proportional to the square of the distance of the source. This is known as the inverse square law, and it gives us a way to calculate what the intensity of the treatment beam would be at a different point than the point at which the intensity is known. What's important to remember about this is if the distance from the source increases, then we know our beam intensity is going to decrease. Conversely, if the distance from the source decreases, then we know our intensity will increase. So, let's look at an example. If we know that our beam intensity at point 1 is 400 centigrade per minute, then our distance at D1 is 100 centimeters. What would the intensity of the beam be at a distance of 250 centimeters from the source? Well, we take our inverse square equation, plug in our known numbers, and we get a value of 64 centigrade per minute. So what we see here is that as the distance increased by a factor of 2.5, the intensity of the beam decreased by a factor of 2.5 squared, or 6.25. Okay, let's talk about treatment setup. Treatment setups fall into two main categories, the SSD setup and the SAD setup, and we'll define those in just a moment. But it's important to know that everything for treatment setup and treatment delivery is designed and based on isocenter of the treatment system. What is isocenter, you say? Well, it's the point in space around which the gantry rotates. It is the origin point of your coordinate system. Isocenter, with respect to the patient, is defined at the time of treatment planning. So we set isocenter when we start the treatment plan, and that will end up determining the couch shifts and the setup of the patient during treatment delivery. Okay, for treatment, we have SSD and SAD treatment setups. SSD stands for source to surface distance, and in this case, it means the treatment is defined based on the distance from the X-ray source to the surface of the patient or the phantom. For SAD setup, which stands for source to axis distance, the treatment is defined based on the distance from the X-ray source to the rotational axis of the treatment machine. Next, we'll switch and talk about dose output factors. These factors allow us to calculate dose in a patient for any point and field size that we're interested in. This is accomplished by taking the dose delivered under calibration conditions and multiplying it by field size, distance, and depth factors, which transform the calibration condition dose into the dose we want at the particular point in the patient that we're interested in. So, what is a dose output factor really? In truth, it's just a ratio of the dose at the point we want to the dose at the calibration point. So every output factor we talk about from now on is going to be really just a ratio of doses. So let's talk about our first output factor, percentage depth dose, or PDD. The PDD is basically the ratio of the dose at a given depth to the dose at the depth of calibration. So we can use this to calculate the dose at a given depth by multiplying the dose at the depth of calibration, which we know, times the PDD value at the depth D for the dose we want to know. So in essence, the PDD is basically the difference in the dose at the two depths. And it depends on the depth in the phantom or patient that you're interested in the dose at, the SSD you used for setup, and the field size you're using for treatment. So note here that the field size is defined at the surface of the phantom or the patient. For each treatment beam energy, we will measure a PDD curve, typically done at the time of commissioning of a machine. What you see from these PDD curves is that as the beam energy increases, that the depth at which maximum dose occurs, here, D max, shifts deeper and deeper into the phantom or the patient. What we see from these curves is typically there's a buildup region at the entrance where the dose builds up from an initial value up to Dmax, and then beyond Dmax, a near exponential fall off of the dose. Why do we see this buildup region in our PDD curves? Well, as the X-rays from the treatment beam interact in the water or the patient, as the energy of those X-rays increases, the energy of the secondary delta ray electrons they create also increases. This means higher electron energies means a higher range of those electrons within the patient or the water. So therefore, the depth at which the number of electrons that's being created by the beam and the number of electrons that are coming to rest at the end of their range, the depth at which those two numbers reaches an equilibrium also moves deeper into the patient. As this equilibrium point moves deeper in the patient, our Dmax also moves deeper with it. You can see here, for our 250 kV orthovoltage X-rays, the range of those secondary electrons is very, very short, so that they reach an equilibrium of being created and stopping very close to the surface. As you go to higher energy cobalt 60 gamma rays, you can see that the equilibrium where the number being created and the number stopping moves deeper into the patient. So you get this point deeper where you have a maximum number of electrons. And then as you go to 20 MV X-rays, that point where the maximum number of electrons is right around your equilibrium is moved even deeper into the patient. And you can see from this red rectangle here, that's what we would define as the buildup region of our PDD curve. One thing to note is that the size of the treatment beam affects the PDD value. So if we were to look at PDD at a fixed depth for our treatment beams, we would see that as the field size increases, that PDD value also increases. For instance here, this effect is very large for lower energy beams, like our 250 kV beam here. We can see as we go from a 20 cm squared field up to a 400 cm square field that the PDD value at 15 cm depth almost doubles. However, as you go up in energy, this effect becomes smaller and smaller. So by the time you're up to the highest energy X-rays used for treatment, this effect is only a few percent. All clinics have tables of PDDs for their machines and for each beam energy used for that machine and for each field size used for that machine, stored somewhere in the clinic. It's either printed out in a binder that's stored in a common dosimetry room or in PDFs on a shared hard drive. These tables would look something like this, where you would have the field size for a given beam, and then you would have the PDD value at each depth for that beam. Sometimes it's just a single beam of a single energy. Other times you have a table for that beam at that energy, but a bunch of different field sizes included within the table. So each clinic has their own tables, which will have their own specific formats. Let's look at an example of how we would use percentage depth dose to determine dose at a given depth within a patient or a phantom. So let's say we have a 10 by 10 centimeter square field set up at 100 centimeters SSD, and at Dmax, the dose of calibration, we delivered 200 centigray. What is the dose that we would have delivered at 10 cm depth in that phantom? Well, we know that PDD is just the ratio of a dose at the depth we want to the ratio of the dose at our calibration depth. And we know that we delivered 200 centigray to our calibration depth, and we want to know dose at 10 cm depth in the phantom. So we would go to our PDD tables, and for a 10 by 10 cm field table, we would look up at 10 cm depth, what is our PDD? Well, it's 66.8% at 10 cm. So we would take and plug those numbers into our equation. So 200 centigray times 0.668 equals 133.6 centigray delivered at 10 cm depth for this beam. And that's how you would use percentage depth dose to determine the dose delivered at a specific depth in your patient or phantom. It's important to note that the PDD is dependent on not only the depth within the patient or phantom, but also the SSD you use to set up for the beam delivery. So typically we measure PDDs at a fixed SSD, but if you're treating the patient at a different SSD, you need to correct for how the PDD is going to change due to this change in SSD. The good news is it's possible to divide out the inverse square term that was built into it when you measured it during commissioning and calibration, and then you multiply in the new inverse square term for the SSD you're using for your current treatment. To correct the PDD so that it can be used at a new SSD value, we use what's known as the Maynard F factor. And like I said, this factor is used to divide out the previous inverse square term, so that's what's built into the PDD at the time of calibration. And then we multiply in the new inverse square term that reflects what it would be for the new SSD that you're using for today's treatment. Here's an example of how to use the Maynard F factor. Say I have a patient set up at 80 centimeter SSD for treatment, but I only have 100 centimeter PDD tables. So I want to know what is the PDD at 10 centimeter depth for an 80 centimeter SSD setup. So we would calculate our Maynard F factor, where we would calculate the inverse square term for our calibration set SSD at 100. We would also calculate the inverse square term for our new treatment SSD at 80 centimeters. The ratio of those two, in this case, would equal 0.963. So what we do, the PDD for 80 centimeter SSD would then equal F, our Maynard F factor, times the PDD at 100 centimeter SSD. So in this case, 0.963 times the PDD for 100 centimeter SSD at the given depth that you want to know the dose at. So let's try to put our Maynard F factor and our PDD concepts together here. So let's say we have our patient set up at 80 centimeters SSD, and if our dose at Dmax, our calibration depth, is 200 centigray, what is the dose for a 10 by 10 cm field at a depth of 10 cm? So we know that our PDD at 80 SSD is equal to our Maynard F factor times our PDD at 100 SSD. So we would calculate our Maynard F factor again. We would divide out our 100 centimeter calibration SSD inverse square factor, and we would multiply in the inverse square factor for the 80 cm setup. And so our dose at our desired depth is just our dose at Dmax times our PDD at 80 SSD. So our dose at 10 cm depth is equal to 200 centigray times 0.963 for the Maynard F factor times 0.668, which is the PDD at 100 centimeter SSD, which would give us a total of 128.7 centigrade. And finally, for our last concept here for this video. Everything I've been talking about so far gives us a PDD value or talks about calibration for square fields. But what happens if the field we want to use for treatment is not a square? What if it's a rectangle or some other shape? Well, there is a method to take a rectangular field shape and determine what is the equivalent size of a square field that would give the same scatter conditions and the same PDD as what you would get for this rectangular field. So this is known as the equivalent square. So basically, it's the size of the square field that produces the same amount of scatter and the same PDD as the given field you're using for treatment. And what you do is you just calculate what's the side of the square that gives the same conditions and the same PDD. And that's just equal to 2 times the length times the width divided by the length plus the width of your rectangular field. So for instance, if we had a 12 by 4 rectangular field, what is the equivalent square field that we would use to look up the PDD value? So using our equation, 2 times L times W plus divided by L plus W, that would give us a 6 by 6 square field. It gives us an equivalent square side of 6. So in the end, we would use a PDD for a 6 by 6 cm squared field to determine our dose. So that brings us to the end of part 1 in our video series. So if you have any questions over anything I've covered, make sure to leave a comment down below and I'll do my best to answer. Also, if you want to see more videos, leave a comment, suggest a topic. I'll make a video and post it. And since this is a video on YouTube, I am morally obligated to let you know, please like this video and subscribe to our channel to support us so we can make more videos for you.